is Adithya, a PhD student at University of Florida, and here I'll be presenting on our NeurIPS 2019 paper on stochastic variance reduced primal dual algorithms for empirical composition optimization. This is a joint work with Jianshu, Chen at Tencent AI Lab. So this is a basic outline of the talk. So in empirical composition optimization problems, this is the objective we are interested in. So this looks like very similar to the standard empirical risk minimization objective function, except that there is an empirical average both inside and outside a nonlinear merit function phi. Why do we care about such problems? So I've given two examples over here. One is known as unsupervised sequence classification that appears in natural language processing applications. Another is known as risk-averse learning problem that appears in finance applications. So in this unsupervised sequence classification, we notice that this log is a nonlinear function. So there is an empirical average both inside and outside this log function over here. And similarly over here, the nonlinear function is a square function over here. And we notice that there is an empirical average both inside and outside the square function. So what are the challenges with solving trying to solve such an composition optimization problem? Here I've written out the full gradient of the objective function with respect to the parameter vector theta. And we observed that it's not easy to get unbiased stochastic um, gradients to apply SGD kind of techniques. And we need to come up with something different to basically use stochastic gradient descent kind of techniques to solve this problem. So this kind of problem has been looked at in multiple papers in the past, but in a specialized setting. So in many of these existing papers, what the authors do is they look at an objective function that looks like this, and we notice that this inner function over here, f theta, is not a function of both outside and inner average as we are looking at in this specific work. So that is the key difference between our problem formulation and the existing problem formulation in previous works. Um, so how do we solve this problem? So we take a novel primal dual approach to solving this composition optimization problem. So by applying this convex conjugate trick, we can reduce this original minimization problem into this min-max objective function that is written over here. Um, so what is cool about this is that there are no more nonlinear composition of empirical averages in this min-max problem over here. We can sample unbiased gradients with respect to both the primal and dual variables. And moreover, the maximization is decoupled with respect to the dual variables so that we can maximize over all the dual variables in a distributed manner. So if we apply the naive batch gradient ascent for what would we do is like we for each of those dual variables we would use this update rule to um, update the dual variables. But however, this can be like very expensive as we see that we'll have to evaluate multiple gradients and also like multiple averages. The first key idea of our algorithm is that we use this decoupled dual maximization to the fact that the dual variables are decoupled to update just a single dual variable in each iteration of the algorithm. So this is like the coordinate ascent technique. The second key idea of this dual update is that instead of using the full gradient with respect to the specific dual variable, we replace it with the stochastic variance reduced gradient using the technique of Johnson and Zhang. Similarly, if we had to update the primal variables using the full batch primal gradient descent algorithm, this is what the update would look like. Once again, this can be like very complex. So what we do is we again use SVRG kind of technique to replace the full gradient with the variance reduced stochastic gradient. And this is what a naive SVRG gradient estimator would look like for the primal update. So given a objective function h theta, which is it can be written as this decomposed sum over here, this is what a SVRG estimator would look like. So theta tilde is like the reference variable here, and faster these reference variables are updated, the better the variance of this SVRG estimators. But updating this primal variables very often and evaluating the full gradients of this primal variables can also be very expensive. So in this paper, we came up with a free full batch gradient update. So what we do here is like without any additional complexity, we are able to evaluate um the gradient with respect to the primal variable, evaluated the most recent dual variable update instead of the reference variable w tilde. So what in the naive SVRG algorithm for primal update, we would have this full gradient evaluated at the reference variable theta tilde and w tilde, but in our algorithm, we came up with a um, free update to get a gradient evaluated at the reference variable theta tilde, but at the most recent dual variable. And this is a consequence of updating a single dual variable in each iteration. And also we exploit the fact that the objective function is linear in the dual variables. Um, so even though SVRPDA2 algorithm, as we will show, converges much faster, it has like high storage complexity. So the free update comes at the cost of storing these gradients for each and every I going from 1 to the next. So in SVRPDA2, what we do is we don't store these variables, and instead, whenever in the SVRPDA2 update, we replace this term with a noisy function f dash zero tilde, which is evaluated xi by ij. So if you're interested more in the algorithm itself, these SVRPDA1 and SVRPDA2 algorithms are in the paper. We obtain theoretical guarantees. So under strong convexity assumption, we show that the algorithm converges at a linear rate, and we also obtain the oracle complexity, which is given over here. So we compared this complexity with existing algorithms. So once again, we consider a more generalized problem that is of this form, and our complexity is also derived for this problem over here. However, the complexity can also be derived for the special problem over here, and we compare the complexities with the other algorithms for the special case, because the other algorithms other papers derive complexity for their algorithms in the special case. And even in this case, we observe that our algorithm has comparable or better complexities in all compared to all composition optimization algorithms. We also write out the storage complexity of both SVRPDA1 and SVRPDA2 algorithms. We also implemented our algorithm on real finance data risk-averse learning problem, and we observed that our algorithms, both SVRPDA1 and SVRPDA2, either have comparable or better performance than all existing composition optimization algorithms. We applied our algorithms for MDP for policy evaluation problem and compared it with a very recent CSAGA paper by Zhang and Shao, which was published in ICML 2019. And we see that our algorithm performs better than the CSAGA paper too, CSAGA algorithm too. And it was shown that we compared our algorithm only with CSAGA because CSAGA was shown to outperform all other existing composition optimization algorithms at that time. So in summary, we proposed new SVRPD8 algorithms to solve generic stochastic composition optimization algorithms, and we derived non-asymptotic bound for the error sequence. We also showed linear convergence, and the complexity we derived was better than all existing composition optimization algorithms. Experimental results showed that the algorithm outperforms all existing algorithms, and also here we write the future extensions. maybe like we want to consider um, solving what happens if the objective function is non-convex, and what if we did mini batches via PDA instead of like doing just a coordinate ascent, single coordinate ascent update, and how acceleration techniques can be used to further improve the convergence rate. Thank you.